Hello viewers, welcome to the next lecture on this book Course on Mathematical Portfolio Theory. You would recall that in the last lecture we started our discussion on the modern portfolio theory and we identified that the two main pillars of modern portfolio theory which characterize it are the expected return and risk, and then we discussed that in the context of the definition of the expected value and variance of a random variable that we had studied earlier. So, we will continue the discussion on this topic and we will now move on to a discussion where we consider a portfolio of several assets and then look at what is going to be the expected return and risk of that particular portfolio. So, just to begin with, a portfolio essentially is a collection of different kinds of assets such as stocks, bonds and other financial derivatives. And the key question that we want to answer in portfolio theory is that what should be the appropriate and optimal allocation of our money that we want to invest in different assets. And you recall that this process involves first figuring out which assets that we would like to invest in amongst the thousands of different alternative choices that we have, and then we look at different portfolios that can be created out of it, and finally, we need to look at what is going to be the best choice amongst all those different portfolios that we would like to make our eventual investment in. So, we begin first with identifying the key inputs that are required in this particular process of portfolio optimization in the mean variance framework. So, accordingly, we start today's lecture. So, during the security analysis, that means the analysis of each of the assets that you are considering for investment, the following data input is required for every security, and let us identify them one by one. First of all, we have what is known as the expected return, and we have already seen what the definition of this. This is E of R I. Next is we will have variance of returns, that is sigma I square, something that you have already seen, and finally covariance of returns between all securities, and which we denote by sigma I j. So, we will begin with the discussion on the tools for portfolio analysis. And the first topic that we will look at is what are known as portfolio weights. So, the portfolio analysis approach will not indicate the absolute currency amount invested in each security, rather we instead it yields the proportion of each security in the portfolio, and so accordingly these proportions or weights are denoted by Wi for security I. So, let me explain this in a little more detail. So, what happens is, suppose that we want to invest an amount of 1000 and then we decide to invest 500 each into different stocks. So, when you talk about a portfolio, we do not identify that by the statement that we have invested 500 in the first stock and 500 in the second stock. Rather, it is customary and the standard approach is to identify by the proportion of the amount of total investment that is invested in each asset. So, instead of making a statement that the investment is of 500 in each of the two stocks, we will instead say that a fraction of half is invested in the first stock and the fraction of half is invested in the second stock, and this number are determined by the amount invested in each stock divided by the total investment. So, I arrived at the amounts half and half by 500 divided by 1000. So, there are of course, another way of how to identify a portfolio would be looking at the number of assets, but again the number of assets will be merged and multiplied with the price of the unit of that asset and divided by the total amount of money that is invested to give the weights for a particular asset. So, for example, if I invest in n assets, in n number of units of the ith asset, and the price of the asset is Pi, and the total investment then is going to be summation I is equal to 1 to say n number of assets, and consequently the weight Wi is going to be number of units of the asset into its price, that is the total amount of money that you have invested in the ith asset divided by summation Ni into Pi I is equal to 1 to n. So, this is a statement that I am making slightly informally before again going back to my formal statements. So, more specifically, so if I can now view weights in the paradigm of this formulation. So, more specifically, Wi is the fraction of the total value of the portfolio that is invested in security I. So, that means it is the fraction of total investment in security I out of the total investment that is made in all the n number of securities. So, assuming that we have invested in n number of securities, the following constraint holds, and this constraint is that summation Wi I is equal to 1 to n is equal to 1. So, if you observe here, this is summation Wi I is equal to 1 to n is simply going to be summation Ni Pi I equal to 1 to n divided by summation Ni Pi I is equal to 1 to n, which is equal to 1. So, essentially this means that all the fractions they have to add up to 1. So, this means that the n fractions, that means W1 through Wn of the total portfolio invested in n different assets adds up to 1. Okay, so now that we have defined what is the weight of a portfolio, or rather the weight of a particular asset in a portfolio, the next thing we need to do is that we need to look at the two characteristic factors that are used to define a portfolio, namely the expected return and risk. So, accordingly we first begin with what is the expected return of a portfolio comprising of S number of assets as just defined. So, we start off with expected return of a portfolio. So, let R subscript P denote the return on a portfolio, and I denote the portfolio by P comprising of n securities. Further, let W I be the weight of security I whose return is R subscript I as defined before. Then we can show that R P is summation W I R I is equal to 1 to n, and accordingly the expected return of the portfolio P is given by expected value of R P, which is expected value of summation W I R I is equal to 1 to n, and this is summation W I E of R I is equal to 1 to n. So, that is, we can now interpret this as the expected return on a portfolio is the weighted average of the expected returns of the n securities, actually I should say a weighted sum of the n securities comprising the portfolio. Okay, now that we have defined the expected return of the portfolio, the next thing we are going to do is make use of that in order to define and then give a formulation for the risk of this particular portfolio P. So, then we start off with the risk of a portfolio. So, let the variance, and I will use the variance as a measure of risk, or equivalently the square root of that which is the standard deviation as a measure of risk. So, let the variance of the portfolio return R P be denoted by sigma p square. Now, we can obtain an analytical expression for sigma p square in terms of variances and covariances of all the securities comprising the portfolio. So, we begin with a simple case and then build upon it. Of a portfolio comprising of two assets, which can then be extended to a n asset portfolio. So, then so we will first look at the two asset case. Then what is sigma p square going to be? By definition, this is going to be the expected value of R p minus E of R p square. Now, we recall the form for R p and E of R p, and we substitute those here. So, accordingly we will get E W R p will be replaced by W 1 R 1 plus W 2 R 2, and E of R b will be represented by W 1 E of R 1 plus W 2 E of R 2 square. Now, I combine the terms involving W 1 and W 2 separately. So, this is going to be, so I will take this term and this term. So, I will get W 1 into E of W 1 into R 1 minus E of R 1 plus W 2 into R 2 minus E of R 2 square. Alright. So, now this can be rewritten as, so this is going to be E of W 1 square R 1 minus E of R 1 square plus W 2 square R 2 minus E of R 2 square plus twice W 1 W 2 E of R 1 minus E of R 1 into R 2 minus E of R 2. So, I can now make use of the linearity property of expectation. So, this becomes W 1 square E of R 1 minus E of R 1 square plus W 2 square into expectation of R 2 minus E of R 2 square plus twice W 1 W 2 into E of R 1 minus E R 1 into R 2 minus E R 2. Now, observe that this is sigma 1 square, this is sigma 2 square, and this is the covariance of 1 and 2. So, this becomes W 1 square sigma 1 square plus the second term becomes W 2 square sigma 2 square, and the third term becomes twice W 1 W 2 into sigma 1 2, which is the covariance of returns of asset 1 and 2. Okay, now we give a slightly different representation and it will be slightly more general in nature to this expression that we have obtained just now. So, another way to express the sigma p square is follows. So, sigma p square is equal to, so I just rewrite this as W 1 square sigma 1 square plus W 2 square sigma 2 square plus twice W 1 W 2 sigma 1 2. Now, I can write sigma 1 square as sigma 1 1, all right, basically covariance between the first asset and itself, and W 1 I can square can be written as W 1 into W 1. Likewise, the second term can be written as W 2 into sigma 2 2 plus the third term can be written as W 1 W 2 sigma 1 2. So, I can decompose this into this factor and W 2 W 1 into sigma 2 1. Now, this step can be collated as double summation I is equal to 1 to 2, j is equal to 1 to 2, W I W j sigma I j, and another representation of this is going to be summation I is equal to 1 to 2 w 1 square sigma w I square sigma I square plus double summation I equal to 1 to 2 j equal to 1 to 2 I not equal to j, that means 2 1 and 2 2, and this will be w I w j sigma I j. So, this basically will collate to these two terms, and this will correspond to this and these terms. Alright. So, now that we are done with the case of two assets, so we now extend the results for to the 3 asset case. So, accordingly, the expected return and variance are going to be given by, so E of R p is going to be W 1 E of R 1 plus W 2 E of R 2 plus W 3 E of R 3. And similarly, sigma p square is going to be E of R p minus E R p whole square, and this is going to be E of W 1 R 1 plus W 2 R 2 plus W 3 R 3 plus W 1 E R 1. So, this should be this minus, so just make this correction, W 2 E of R 2 plus W 3 E of R 3 square. And this again can be rewritten as W 1 square E of R 1 minus E R 1 square plus W 2 square E of R 2 minus E R 2 square plus W 3 square E of R 3 minus E of R 3 square plus twice W 1 W 2 E of R 1 minus R 2 E of R 1 into R 2 minus E of R 2 plus twice W 2 W 3. So, this is going to be E of R 2 minus E of R 2 into R 3 minus E of R 3 plus twice W 1 W 3. This is going to be E of R 1 minus E R 1 into R 3 minus E of R 3. So, this can be now rewritten as W 1 square sigma 1 square plus W 2 square sigma 2 square plus W 3 square sigma 3 square, and this term is going to be twice W 1 W 2 into sigma 1 2 plus twice W 2 W 3 sigma 1 3 plus twice W 1 W 3 sigma. So, this is actually sigma 2 3 and this is sigma 1 3. All right. So, which can be represented as sigma p square is summation W I square sigma I square I is equal to 1 to 3 plus double summation I equal to 1 to 3 j is equal to 1 to 3 I not equal to j W I W j into sigma I j. So, in conclusion, so in general we have sigma p square is equal to summation W I square sigma I square I is equal to 1 to n plus double summation I is equal to 1 to n j is equal to 1 to n I not equal to j W I W j into sigma I j. So, this is nothing but I am just rewriting the formula for the variance of the linear combination of n number of random variables that we had seen earlier. Okay, so we next come to something which is known as the opportunity set, and we will discuss briefly about that. So, let me begin with opportunity set. The opportunity set also referred to as the feasible set comprises of all the possible portfolios that can be formed out of n securities. The set of all possible portfolios formed from a group of n securities lies either or within the boundary, either on or within the boundary of the opportunity set. The opportunity set can be plotted in the sigma ER space. So, just to do a recap of the opportunity set, I have made two observations. The first is that the opportunity set, which is sometimes is called the feasible set, it comprises of all the possible portfolios that can be formed out of the n securities. So, essentially this means that if you have n number of securities, you can choose different combinations of weights for each of those securities in the portfolio, of course, provided that the sum of the weights is always equal to 1. So, that means it is going to be a combination of some W 1 through W n such that summation of W I equal to 1 to n is equal to 1. So, this effectively basically gives an infinitely many different possibilities of such portfolios, and the collection of all these portfolios is what is known as the feasible set. Now, in particular what you can do is that, now if we consider n number of assets, then for large number of n's it is very difficult for us to visualize this vector W 1 through W n, that is the vector of the weights. So, equivalently what it can do is that for each combination of W 1 through W n, we can use this formula and previous formula, that is E of R p is equal to summation W I E of R I is equal to 1 to p. So, for each combination of W 1 through W n, what I will have is I will have a pair of the sigma and E. So, instead of so the feasible set, instead of being represented by this vector W 1 through W n, which obviously cannot be drawn on a n dimensional plane, we equivalently represent this by their corresponding sigma as given here and the corresponding ERP as given here. So, graphically this will look something like this. So, says if you have, for example, so you can actually see this in the context of a 2 asset portfolio. So, if you have the weights W 1 and W 2 satisfying the condition, say W 1 plus W 2 is equal to 1, then corresponding to each pair W 1 and W 2, we can use the formula to calculate E of R p and sigma of R p, and they will basically comprise of these particular points. So, for example, if I choose a W1, W2 from here, the corresponding sigma, which actually is sigma p, and the corresponding E of r, which is basically E of r p, this might be this point here. Likewise, if I choose this pair of W1, W2, the corresponding value of ER and sigma in the ER sigma diagram, this could be here. So, essentially the set of feasible portfolios actually is the combination of all these W1s and W2, but because it is going to be very difficult to visualize them on a n dimensional plane. So, they are equivalently visualized by their corresponding values of sigma and ER, and a lot of times this is what is known as the ER sigma diagram, or sometimes it is called the mu sigma diagram. So, we will discuss more of this later on when we talk about efficient frontier. So, let us now come back to the case of two securities. Now, for two securities, what did you have? So, we recall that E of R p is equal to W 1 E of R 1 plus W 2 of E of R 2, and sigma p is going to be square root of the variance. So, which was W 1 square sigma 1 square plus W 2 square sigma 2 square plus twice W 1 W 2 sigma 1 2, and this can be rewritten as square root of W 1 square sigma 1 square plus W 2 square sigma 2 square plus twice W 1 W 2 rho 1 2 sigma 1 sigma 2. So, what I have done here is we have made use of that rho 1 2 is equal to sigma 1 2 over sigma 1 sigma 2, and I replace sigma 1 2 with rho 1 2 sigma 1 sigma 2. Okay, so, basically the set of feasible set is not represented by this W 1 and W 2, but rather it is represented by this E of R p and sigma p. Okay, so, now so this can be extended to n securities. So, next we come to minimizing the risk. And this will be again for two securities portfolio. So, this topic of minimizing the risk is going to be the first topic on portfolio optimization, on how we determine the portfolio once we have decided what is going to be the asset that will constitute the portfolio. And for the sake of brevity, I will start off with considering a two asset portfolio. And the goal is that I want to look at the situation that amongst the different assets, that means amongst all the feasible assets that I have just now defined in case of this two asset portfolios, which is the one that is going to give me the minimum risk. So, later on we will look at a more generalization of this, that it is going to be no longer just the minimization of the risk, but we will also talk about minimizing the risk for a given set of return, or maximizing the return for a certain level of risk, and all of this will be collated to form what is known as the concept of efficient frontier. So, coming back to this very elementary and the first step in determining what is going to be the best choice of my portfolio in case of a portfolio comprising of two assets, we will just focus on minimizing the risk. So, while you are doing the minimization of the risk, we will essentially make use of single variable calculus. So, let us come to the minimization of the risk. So, the weight that rather weights, because there are two assets. So, the weights that minimize the variance. So, please remember the minimization of the standard deviation is effectively the same as minimization of the variance. So, that minimizes the variance of a portfolio can be obtained. So, I should specify that this is a two security portfolio. So, this can be obtained using single variable calculus. Accordingly, we take the first derivative of the variance of the portfolio with respect to weight W1 of asset 1. Now, please remember that the minimization of this variance will be to determine the values of W1 and W2, which is going to give me the minimum value of sigma p square. Now, we note that here I have to determine the two values W1 and W2. So, it is effectively minimization of a function in terms of two variables W1 and W2. But I am saying that I will basically make use of single variable calculus here. Now, for that purpose we need to recall that we had the condition that W1 plus W2 is equal to 1. So, this means that I can replace W2 with 1 minus W1 and put that in the expression for sigma p square. So, this will result in the expression for sigma p square no longer being a function of two variables W1 and W2, but rather it is going to be a function of one variable, namely W1. And once I have found out what is the optimal value of W1, obviously the corresponding W2 given by 1 minus W1 is going to be the minimum variance weight for the second asset. So, accordingly we do the following. So, we start off with that, then note that what is sigma p square? Sigma p square was W1 square sigma 1 square. Then I had W2 square sigma 2 square, so which are replaced by 1 minus W1 square. Then I had plus twice W1, and then I will multiply this, replace W2 with 1 minus W1 into sigma 1 2. So, now I take the partial derivative of this with respect to W1. So, this is going to be the derivative of W1. So, actually I can just take the ordinary derivative since it is a function of single variable now. So, dp sigma square into dW1. So, this is going to be ddW1 of W1 square sigma 1 square plus 1 minus W1 square sigma 2 square plus twice W1 into 1 minus W1 into sigma 1 2. So, this turns out to be equal to twice W1 sigma 1 square from this term. Then I will have a minus 2 into 1 minus W1 into sigma 2 square from this term, plus I will have 2 into 1 minus twice W1 into sigma 1 2. And in order to determine what is the maxima and the minima, or the value of W1 at which this will be a minima. So, we will have solving for W1, we can get that this is equal to sigma 2 square minus sigma 1 2 by sigma 1 square plus sigma 2 square minus twice sigma 1 2, which implies that W2, which is 1 minus W1, this is going to be sigma 1 square minus sigma 1 2 divided by sigma 1 square plus sigma 2 square minus twice sigma 1 2. And you can do the second derivative test also, that here you can take the second derivative and you can show that the second derivative of this expression, this is going to be greater than 0 by making use of the properties of the first and second moments as well as the properties of covariance. Okay. So, essentially what you have obtained is that the portfolio, so if I have two assets and I am in a dilemma as to choose what is the proportion or the weights that I should assign to each of those assets, Then if I set my goal that I want the asset with the minimum risk as given by the variance or equivalently standard deviation, then it turns out that the weights for that minimum variance portfolio is going to be W1 and W2 as given by this expression here and this expression here respectively. And you notice that both this expression, what are the quantities it involves? It involves sigma 1 square, sigma 2 square and sigma 1 2, which are the variances of the two assets as well as the covariance of the returns of those two assets. And these are the numbers that we have already seen how you can determine from the historical data. So, you basically once you decide on two assets, then you can make the historical use of the historical data and you can just substitute those numbers here and decide what is going to be your optimized portfolio. So, this is a very simple way in which you can actually download the data that is available publicly and make a decision on how you are going to set up your portfolio based on this optimization. Okay. So, now let us move on to minimizing the risk in case of a 3 asset portfolio, and eventually we will look at an n asset portfolio. So, I look at minimizing the risk for 3 asset portfolio. So, for the 3 asset portfolio, you recall that E of R p is going to be summation W I E of R I is equal to 1 to 3. Now, we need to figure out what is going to be the sigma p square. So, here we recall that the sigma p square is W 1 square into W 2 square into sigma 2 2 plus W 3 square into sigma 3 3 plus twice W 1 W 2 into sigma 1 2 plus twice W 1 W 3 into sigma 1 3 plus twice W 2 W 3 into sigma 2 3. Now, what I can do is that I can make a substitution by replacing W 3 is equal to 1 minus W 1 minus W 2. So, accordingly what this will become is this is going to be sigma 1 1 plus sigma 3 3 minus twice sigma 1 3 W 1 square plus twice sigma 3 3 plus twice sigma 1 2 minus twice sigma 1 3 minus twice sigma 2 3 W 1 W 2. These are the cross terms, plus sigma 2 2 plus sigma 3 3 minus twice sigma 2 3 into W 2 square plus minus twice sigma 3 3 plus twice sigma 1 3 into W 1, linear term in W 1, and minus twice sigma 3 3 plus twice sigma 2 3 W 2, that is the linear term in W 2, plus sigma 3 3. Now, what is my goal? My goal here is to basically figure out what is going to be my values of W 1, W 2 and W 3 that is going to result in getting the minimum variance sigma p square. And now, I have reduced this, instead of being it a function of 3 variables W 1, W 2 and W 3, by making the substitution that W 3 is equal to 1 minus W 1 minus W 2, I have reduced this sigma p square to be a function of 2 variables, namely W 1 and W 2. So, in order to determine what is going to be the optimized value of W 1 and W 2 and obviously consequently W 3, I take the partial derivative of the variance with respect to W 1 and W 2 and set it equal to 0. So, accordingly I get delta sigma p square delta W 1, this is going to be twice sigma 1 1 plus sigma 3 3 minus twice sigma 1 3 into W 1 plus twice sigma 3 3 plus twice sigma 1 2 minus twice sigma 1 3 minus twice sigma 2 3 into W 2 plus minus of twice sigma 3 3 plus twice sigma 1 3 W 1 and set it equal to 0. So, this coefficient comes from here, and this one it comes from this term, and this one comes from this particular term, and I set it equal to 0. Likewise, I will set delta sigma p square delta W 2. This is going to be, so I will get twice sigma 3 3 plus twice sigma 1 2 minus twice sigma 1 3 minus twice sigma 2 3 into W 1. So, it is again from this term, plus twice sigma 2 2 plus sigma 3 3 minus twice sigma 2 3 into W 2, which comes from this term, and I will then have minus twice sigma 3 3 plus twice sigma 2 3 from this term, and this is set equal to 0. So, I call say this equation 1, and I will call this as equation 2. So, if I solve equation 1 and 2, remember that these are linear equations in W 1 and W 2. Actually, there is no W 1 here. So, please make this correction. And here I have W 1 and W 2. So, I solve this equation for W 1 and W 2 and call them say W 1 star and W 2 star. Then W 3 star is going to be 1 minus W 1 star minus W 2 star. So, this W 1 star and W 2 star and consequently W 3 star are the weights in a 3 asset portfolio that minimizes the variance of the 3 asset portfolio. So, in general, if you want to extend this to an n dimensional or an n asset portfolio, then obviously you can guess that the calculations are going to be much more cumbersome, and for that point of time we need to look at some alternative methods to figure out how you are going to determine W 1 star, W 2 star all the way to W n star in case of a n asset portfolio. All right. So, just to conclude whatever we have discussed today, in today's class we started looking at by talking about the 3 key data input that is required when you are doing a portfolio optimization. And then we talked about what is going to be the return. First of all, we talked about what is the weights, and this consequently gave us what is the definition of the return of a portfolio in terms of weights and the returns of the individual assets that constitute the portfolio. And then we took the expectation and the variance for both of them to calculate what is going to be the expected return and variance for a 2 asset portfolio, for a 3 asset portfolio, and in general for a n asset portfolio. And then we talked about what is a feasible set, and then we started our discussion on how among a feasible set of portfolios we can choose the one that is the best, and by best we could basically have different meanings. To begin with, we define that the best portfolio amongst the feasible set, we are choosing the one that will minimize the risk, and accordingly we have determined the weights of a portfolio such that the risk of that portfolio comprising of those assets are obtained in case of a 2 asset portfolio and in case of a 3 asset portfolio using single and multivariable calculus respectively. So, we will extend this in the next class and discuss this in a lot more detail. So, this concludes this lecture for today. Thank you for watching.